Right now, in the time it takes you to watch this video scene, electricity has traveled possibly hundreds of kilometers, changed voltage several times, and arrived at your wall with zero delay. No warehouse, no inventory, no stockpile sitting around waiting. Here is the engineering story behind how that actually happens. It starts with a question. Why is your power made so far from where you live? Part of it is simple. Nobody wants a power plant next door. So cities push generation outward. But that's not the real driver. The real reason is that a power plant can't just be built anywhere. It has to be built wherever its energy source physically exists. A hydro plant needs a river with the right drop in elevation. A coal plant needs to sit near the coal seam or the rail line hauling it in, because fuel is heavy and expensive to move. Wind farms go where the wind is strongest. Solar farms where land and sun line up. And nuclear plants obviously need a massive, reliable source of cooling water plus a wide safety buffer. Cities, meanwhile, grew up around rivers, harbors, and farmlands for completely different reasons. So the map of where people live and the map of where energy sources exist almost never overlap. That mismatch is the starting problem the entire electricity grid was built to solve. And it's made harder by something even more fundamental. Electricity cannot be stored at scale. Unlike water in a reservoir or grain in a silo, the power a plant generates has to be consumed at virtually the same instant it's made. So now you have two problems stacked on top of each other. Power is made far from where it's needed, and it has to get there in real time, continuously, with no buffer. That combination is exactly why transmission lines exist. Here is a puzzle those lines had to solve. How do you move enormous amounts of problems, hundreds of kilometers, through a simple metal wire without losing most of it as heat along the way? The answer comes from two equations every electrical engineer learns early on. First, Ohm's law, V equals I times R, and the power lost as heat in a wire, P equals I squared times R. Notice that second one, loss doesn't scale with current, it scales with current squared. Double the current and you don't double the losses, you quadruple them. Half the current and losses drop to a quarter. That single relationship shaped the entire architecture of the grid. If you need to deliver a fixed amount of power, the smart move is to push current down and let voltage carry the load instead. So at the power plant, transformers step voltage up, sometimes above 400,000 volts, while current drops correspondingly, and that high voltage power travels across the long distance lines you see on steel towers, losing far less energy than it would otherwise. But 400,000 volts obviously can't come into your living room. So as power approaches cities, substations step it back down in stages. First for regional delivery and then for neighborhood, until it finally reaches the 120 or 240 volts your outlets use. That handoff to your neighborhood is where the hardest part of the whole system actually lives. Distribution. Transmission is long distance, but relatively simple. Big wires, few endpoints. Distribution is the opposite. Short distances, but millions of endpoints. Every one of them needing continuous, tightly regulated power with almost zero tolerance for interruption. This is the layer with the transformer on the pole outside your house. the underground cable network, and the protection systems that isolate a fault fast enough that one fallen branch doesn't take out an entire neighborhood. It's less raw physics and more precision and redundancy. Honestly enough for its own entire video. So the next time you flip a switch, here is what actually happened. A generator possibly hundreds of kilometers away, sitting wherever its fuel or resources forced it to be, adjusted its output in real time to match your exact demand. No storage, no delay, funneled through a system built entirely around one equation. P equals I squared R. That's the real journey behind something we never think twice about. If you want the next video to go deeper how transmission lines are engineered or how disruption grids self-heal during faults, let me know in the comments and subscribe if you want to keep going down this rabbit hole. Thanks for watching.